On Friday, we discussed the kind of review stuff for exponential equations. All right. So there were two main formulas that we talked about. So remember, the parent function of an exponential function is y equals a times b raised to the x power, where a is your y-intercept, b is your base, x is your exponent. All right. Now, there were two formulas that we talked about. We talked about growth and we talked about decay. Does anyone remember what the general growth formula is? So what's the formula for exponential growth? You guys are missing some parts. A equals what?
P parentheses 1 plus R parentheses and then the next one.
Good.
Yeah,
We're just doing the warm up right now. So we're about to do. All right. Now that's growth. Now, what does the A stand for? Amount or accumulated. So basically, whatever your amount is after the time period. What's P stand for?
principal.
Stands for principal, which is just a big fancy word that means what? Starting amount. What's R stand for? Rate. Now that rate's usually given a percentage, but how do you put it in the formula?
As a decimal.
You have to put it as a decimal. And T? Time. Now, what's decay? Shh. What's decay?
A equals P parentheses 1 minus R parentheses and exponent.
Good. So, pretty much the exact same thing as growth. The only difference is one has a plus, one has a minus. All right? Now, this problem right here is either going to be a growth or a decay. So it says the population of llamas is stranded on a desert island is decreasing due to a food shortage by 6% per year. If the population of llamas started out at 350, how many are left on the island after 10 years? So first off, we got to identify which formula we're using. Is this going to be an exponential growth or a decay? Decay. Why? Someone hasn't talked yet. I heard it. It says decreasing. Keyword, decreasing. That means we're going down, which means decay. So we're using this formula. Now, I always say go ahead and define what each of your variables are. So all I got to do is just plug it into the formula. So A is what we're trying to find, so we're just going to leave it as A. What's P? So what did I start with? 350. Good. What's my rate of decrease?
0.6.
Not 0.6.
Oh, 0.06.
Right. So it's 6%, which as a decimal is 0.06. Remember, if you don't remember how to convert between percentage to decimal, all you do is just take whatever the percentage is divided by 100. There's your decimal. Time. How much time do they want to pass? 10 years. So I'm going to take all of that and plug it into my function. So I have A is equal to 350 times 1 minus 0.06, all raised to the 10 power. Now, if I want to simplify this a little more, I can simplify what's in the parentheses. So A is equal to 350 times 0.94 raised to the 10th power. Now, something I didn't talk about last week that you do need to know. This decimal right here is known as your rate of decay. Or decay rate, either way. But right here, this number in the parentheses is known as your decay factor. So what that means is that every year that passes, we're only keeping 94% of that population. All right? So for example, after 1 year, we're only keeping 94% of the 350. Then after another year, we take whatever number we just got Take 94% of that, that's our new population after 2 years. All right, does that make sense? All right. So the rate of decay is how much we're decaying by. The decay factor is what we're actually, how much of the population we're actually taking each time. All right, or how much of the money we're taking each time, or keeping, however you want to think about it. Now, remember what I said, you just got to put this in your calculator and get an answer. So, round to the nearest whole number. What'd you guys get? 189 llamas. So after 10 years, there's only going to be 189 llamas left. All right, so these are the very, very easy rates and growth and decay problems. All right, which you guys did pretty well on last week. Okay, so now we're going to take it a step further. We're going to talk about some other types of exponential word problems that you may see, but they're very, very similar to these. All right, so we're going to start first with doubling and half-life, and we're going to go into compound interest. All right, so go ahead and take out your packet. I'm about to tell you the page. Give me 1 second. All right, let's do page 7. All right, so that should be the top of your page. So let's say 2.2b. All right, boys. Guys, go ahead and clamshell your laptops for me unless you're using it for the OneNote. So if you're using it for the OneNote, you can keep it open, but otherwise clamshell them. All right, so we're still dealing with growth and decay problems. It's just going a step further in terms of doubling and halving. All right. So, guys, please stop talking. It's going to become an issue. I'm going to have a seating chart. Now, there is a phenomenon where the percent increase or decrease per time unit, and a lot of it can be physically modeled by exponential equations. So a lot of times this is population or radioactivity or money. All right, these are the main 3 phenomena that we deal with exponential functions. Now, exercise 1 states a colony of fruit flies has a population that doubles every 8 hours. There are 22 fruit flies in the initial population. So, it's saying its population completely doubles every 8 hours, which means after one set of 8 hours, how many fruit flies are you going to have? 44. After 16 hours, how many will you have? 88. All right. So it doubles every 8 hours. That's what it's saying. So we're first going to write P as it represents the population of fruit flies. D represents the number of times the population has doubled, and P as the function of D. So, first off, do you guys think it's going to be an exponential growth or decay problem? Growth. So we're still using A equals P times 1 plus R to the T power. So we're just going to do this like we've been doing. So A in this case is going to be P because they want P to represent the population. Now, our principal, how many fruit flies did we initially start out with? 22. Now, our time is just going to be how much it doubles, so we're just going to call that D. Now, our rate. Here's my question. Think about this logically. If you're doubling the population, how much of the population are you adding on to itself? So in other words, what do you think the rate of increase would be? So that's percentage. What do you think the rate of increase would be? 100. I heard it. It's 100%. So because, think about it, every 8 hours, we're taking 100% of 22, which is 22, adding it to 22, which is 44. All right. So what's 100% as a decimal? It's just 1. So if I plug this in, I have P is equal to 22 times 1 plus 1 raised to the D power. And then what's 1 plus 1? 2. So this would be the equation I come up with. So if you see a 2 as your base, it's still representing a growth problem, but the rate of increase would be 100%. All right? Because we're doubling. Now, let's say that H represents the number of hours since the population was originally at 22. So D currently represents how many times we doubled. So like, let's say we doubled once, we plug in a 1. That means we're doing 22 times 2. All right? Now, what is the equation that relates H to D? We want to solve this equation in terms for D in terms of H. So let me ask you guys this. All right. So we want to know how many hours is happening for every time we double. So if we double once, how many hours have passed? 8. If we double twice, how many hours have passed? 16. So how do you think? So 1 double, that's 8 hours. 2 double, that's 16 hours, so on and so forth. So my question is, if H is equal to the number of hours, how can I write that as an equation in terms of D? So in other words, D is how many times we doubled. H is the number of hours that have actually elapsed. So we basically already did it. So what do you think in terms of D? How would I write H? Backwards. H equals 8D. Because if we take the number of times we doubled, so let's say we doubled twice, we multiply that by 8. That's how many hours have elapsed. Because 8 times 2 is 16. If we doubled 3 times, 8 times 3, that's 24. All right, that's what this means. Now, if we wanted to solve for D, what's the only thing I got to do to solve for D? Divide by 8. So D is equal to H over 8. Now, why is this important? Well, sometimes it's going to ask us. So sometimes it may ask us, okay, well, how many fruit flies are there after 12 hours? Does 12 go into 8? Or does 8 go into 12, I mean?
Yes. Oh, no.
No, it doesn't. It doesn't go in nicely. So, but we can still figure it out using what we just came up with. So what we're going to do is using our answers from A and B, so this one and this one, we're going to model for the population of fruit flies, P, as a function of the number of hours since they were 22 flies. So what we're going to do is we're going to take this H over 8 and substitute it in for D. So we're just going to replace D with H over 8. So this would be P is equal to 22 times 2 raised to the H over 8 power. Now, we're not done because we essentially want to write it so that it looks like just an exponential growth equation that we're used to. And here's how you do it. Now, h over 8 is the same thing as what number multiplied to h? So h over 8 is the same thing as what number being multiplied to h? So h over 8 is equal to some number times h. What number? Not 8. So if I divide by 8, that's the same thing as multiplying by what? So if I divide by 2, that's the same thing as multiplying by what number? Come on, guys. If I divide by 2, that's the same thing as multiplying by what number? 1/2. So if I divide by 8, that's the same thing as multiplying by what? 1/8. All right. So we're going to rewrite this so that h over 8 is 1/8 h. So we have p is equal to 22, 2 to the 1/8 h. Now, why did I do that? We want to get it so that the h is by itself in the exponent. So what we're going to do is we're going to do the power rule with the 1/8. So we're going to take 1/8 and multiply it to the exponent connected to that 2, which in this case is 1. So this will be p is equal to 22 times 2 to the 1/8 h. And then finally, we're just going to put in our calculator what 2 to the 1/8 is. All right, so can someone do 2 raised to the 1/8 power and tell me what it is? I think it's going to be like a decimal. $1.10105. All right, good. So again, if you need to see it on the board, you do 2, hit the caret key, parenthesis, 1 divided by 8, close the parenthesis. All right, so I'm just going to round this to 3 decimal places, so 1.091. Let's call it that. So this would be P is equal to 22 times 1.091 to the h power. So this equation right here is the equation that we would use to find how much the population grows per hour. So this original was based off of doubling. We then wrote it in terms of hours, which just means we took how much doubled. We could write the hours in terms of 8 times the doubling, so that means the doubling can be written as h divided by 8. We then replaced that in our function, broke it apart, and multiplied that fraction to the exponent. So we raised that base to the 1/8 power. All right. That then gave us our new growth factor. So essentially, what will be the rate of which we're actually growing per hour? Which is the next question. So what percentage of the fruit fly population is increasing per hour? So think back to the exponential growth formula. This one right here. So our rate would be in the parentheses, okay? So we have 1 plus r right here. So this number right here is 1 plus r. So how do you think I can get r? Subtract the 1. So 1 plus r is equal to 1.091. And we're going to solve for r. So we're just going to subtract the 1 to both sides. So the rate is equal to 0.091, which is what as a percentage? So r is equal to what as a percentage? 9.1%. So every hour, the population is increasing by 9.1%. Does everyone understand what I did? So we started with doubling, which doubling, it completely doubles the population every 8 hours. However, if we go off of per hour, it's only increasing by 9.1% per hour. All right. So this is the rate per hour. So what we're actually doing here is changing the model to fit the units of time. So originally it was with doubling, and then we changed it so that it was per hour. So the first equation we came up with right here, this is per how many times we doubled. This equation was when we initially changed it to be per hour, but then we had to finagle it a little bit to get it so it looks like a regular exponential growth problem like we're used to. So I can plug in any number in for h, so 12, 13, 100, whatever. Even if it doesn't go nicely into 8, and I will get what the population is after that many hours. Does that make sense to everyone? All right. Let's look at a different one. So the thing about these models is as long as we're careful when we set up our models, we should be able to move from one unit of time, like doubling, to another unit of time, like hours. So that's essentially what we just did. We went from doubling to hours. So let's look at exercise 2. So a radioactive material has a half-life of 35 years. All right. So you may have learned this in like chemistry, maybe even physics or physical science. All right. AO represents the original amount of it present, and T represents the number of years it has been since decaying. Which of the following models the amount A of the radioactive material still present after T years? So, first off, does anyone remember what half-life means? So in other words, after 35 years, what's going to happen to your initial amount of radioactive material? So for example, if I had 100 grams of radioactive material, how much would be left after 35 years? 50, because we halved it. That's what half-life means. So in other words, if we wrote this equation, it's obviously a exponential decay. All right, because it says the word decaying. So what do you think my rate of decrease will be if we're halving it? Well, what's half of 100? 50. So my rate of decay in this case is actually 50%. So we're only left with half of it. We only keep half of it after 35 years. Now, we fill in the rest. A is just going to be A of T, which is whatever material is left over after that amount of time. P is going to equal our initial, or A subscript 0. And T, we're just going to leave it as T for right now. Actually, let's call T right now H for half-life. All right. So if I plug everything into my equation, I have A of T is equal to A of O 1 minus 0.5 raised to the H power. So H is the number of times I half my population. All right, so that's in terms of 35. So if it halved once, 35 years have passed. If it halved twice, 70 years have passed, so on and so forth. If I clean this up a little bit, I get A of T is equal to A of O 0.5 H. Now, here's my question. How would I figure out figure out how much t years have gone by. So in other words, if I halved it twice, how do I figure out how many years have gone by? So how many years does it take for it to halve? 35. So if I halved it twice, how many years have gone by? 70. How'd you get that? 35 times 2. So if I wanted to find t years equals what in terms of half-life? What'd you just tell me you did? You did 35 times 2, right? So it'd be 35 times h. So 35 times the number that we halved it. So if we halved it 3 times, that would be 105. All right? Or 105 years. So how would I define h in terms of t? So in other words, how would I solve for h for that equation? So how do I get h by itself over here? Divide both sides by 35. So I get t over 35. So that's what I'm going to plug in for h here. So I get a of t is equal to AO 0.5 t over 35. So the equation I'm going to use is 2. Now, 3 and 4 we could have automatically eliminated because that's a doubling, not a half-life. All right? But you got to be careful with how you compare your units. So in some occasions, you'll be multiplying by whatever your years of doubling or years of halving are. In some occasions, you'll be dividing it by it. So my suggestion is think about it in terms of each other and then solve for the one you're trying to find. Now, if the model from exercise 2 was placed into this form, so in other words, we want to get t by itself, then what would be the value of b to 4 decimal places? So we're going to do exactly what we did in the previous problem. So I'm going to take a of t is equal to AO 0.35, 0.5 t over 35. So the first thing I need to do is break apart the t over 35 into a fraction times t. So dividing by 35 is the same thing as multiplying by what? 1 over 35. So I'm going to rewrite that first. So I have a of t is equal to AO 0.5, 1 over 35 t. Then I'm going to use the power rule and multiply that to the exponent with the 0.5, which in this case is a 1. So I got a of t is equal to AO 0.5, 1 over 35, all raised to the t power. So put 0.5 raised to the 1 over 35 power into your calculator. Tell me what it is to 4 decimal places. It's what? 0.980 what? 03. So this would be our equation in this form. So our b value is right here. So, So b is equal to 0.9803. Now, what does that tell us about the decay per year? So how much are we actually decaying a year? So here's my question. This is equal to 1 minus r. all right, because it's a exponential decay problem. So within the parentheses is equal to 1 minus r. How can I solve for r? So subtract 1. So that'll be, what's 0.9803 minus 1? You guys got calculators, use them. Negative 0.0197. Now we're not done because I still got a negative r. So what do I need to do? Divide by negative 1. So this will be 0.0197 is equal to r. So what's r as a percentage? .97% is equal to r. So in other words, what's this mean in terms of the decay rate? We are decreasing by 1.97% per year. So in other words, the radioactive material is decreasing by 1.97% per year. The other way you could write it is based off of the growth factor, or we keep 98.03% of the material each year. So we lose 1.97% per year, but we keep 98.03% of it a year. So guys, in other words, say we had 100 grams of material. All right, we lose 1.97%. So we lose 1.97 grams of it. So what we're left with is 98.03 grams, because that's 98.03% of that number of grams. Does that make sense? Kind of, sort of, maybe. So this is what we're actually decreasing by. This is how much we're actually retaining. They go hand in hand. If you add them up, it equals 100. All right. Any questions on exponential growth and decay? All right, one more and then we're going to move on. So, exercise 4. So, the number of people who know a rumor as a function of days since it started is given by this function. So, we're going to write a model for the number of people who know the rumor as a function of hours, h, that it's spreading. So, what percent to the nearest tenth is the rumor growing per hour? So, we got this function right here, but it's written in terms of days. We now want to rewrite this function in terms of hours. All right. So here's my question. Which is bigger, days or hours? Days. All right. So, in other words, if I were to write it in terms of hours, so if I want to know how many hours have passed after so many days, what do I do to find it? So, for example, how many hours have passed after 1 day? 24. How many after 2 days? 48. How many after 3 days? What are you essentially doing? Well, you add 24 each day, but if I just gave you a random day, so like let's say 100 days have passed, how many hours is that? 2,400. What'd you do? You multiply the number of days by 24. So hours is equal to 24 times the number of days. Now we're going to solve that in terms of D. So how do I solve for D? Divide by 24. So I'm going to take, so D is equal to H over 24, which I'm going to replace in for this D. So I now have N of H, so I want in hours, is equal to 5 times 3.8 times H over 24. But we're not done because remember we need to find the new growth factor. All right. So to do that, we got to separate the H over 24 into a fraction and H. So if we divide by 24, the same thing as multiplying by what? 1 over 24. So we have N times H is equal to 5, 3.8, 1 over 24, H. We then use product rule to multiply the 1 over 24 to the exponent of the base, which in this case is 1. This would be N of H is equal to 5 times 3.8 raised to the 1 over 24 power to the all over to the H power. Now, do 3.8 raised to the 1 over 24 in your calculator and tell me what it is to the nearest tenth. So 1 decimal place. Yes. Yeah. 1.1. So this would be N to the H is equal to 5 times 1.1 to the H power. So this is our growth factor. But we want to know what our rate of growth is per hour. So how do I find that? So what's 1.1 equal to in terms of our formula for growth? What's the 1.1 replacing in terms of our growth formula? 1 plus R. How do I solve for R? Subtract the 1. So I get 0.1 is equal to R. So what's that as a percent? 10%. So we're growing at 10% per hour. So that's how much the rumor is spreading per hour. It's spreading 10% more per hour. So does everyone understand what I'm doing to change the units? It's not too bad, right? You just got to think about it logically. You just got to think about it how you would switch between the units. That's essentially all you're doing. Okay, so in other words, if I'm trying to figure out if I'm trying to switch between minutes and hours, how would I figure out how many hours are in a minute? I'll take the number of hours I have and then divide it by what? Well, how many? 60. Because how many minutes are in an hour? 60. There you go. So if I want to know how many minutes were in that hour, I would take the number of minutes, multiply it. Or no. I did it backwards. I would take the number of minutes and divide it by 60 to get how many hours. I would do 60 times the number of hours to get the number of minutes that elapsed. That's why I say be careful, think carefully what you would actually do. All right, so here's what we're going to do. I'm going to give you guys a 4-minute break because a lot of you are conking out, but we're not done with notes yet. All right, still got a little bit more. We're behind, guys. I got a test by next Tuesday. All right, so we got to kind of hit the ground running with this unit. So I'm going to give you guys a 4-minute break. When we come back, we're going to do 2.2C, but 2.2C is very, very quick. All right, so go ahead. Take a break.
We stuck you with Mr. Michael. No. Forever.
How would you know what you're doing if it's 8 question?
No. I haven't checked. Yeah, it says no school, so we're doing nothing today. Because we got nothing today. It says no school. Oh.
What, you never heard that sound before?
What's many times? I'm shocked.
Maybe it's just you.
I'm here for you. Exactly.
You know,
Just looking.
no. Hey guys, stop on.
Guys, I'm SpongeBob.
Yeah, like, no, you always this. You kept opening your mouth. Yeah. You can tell me.
I was going
My head is tricky. Why do you
keep reading
that was one?
What? Cell phone. I'm reading it. Cell phone. Yeah. I really want to see.
Nine, 8, 7, 6, 5, 4, 3, 2, 1.
All right, guys, let's come back together. This next part's a lot shorter than what we just did, all right? But I got to get through it today. So I'm sorry. Today's kind of a note-heavy day. Tomorrow won't be as bad, okay? All right, so go to page 11. Yeah. Yeah. All right. The last thing we're going to talk about today is the last modeling scenario, which is compound interest. All right. This also is also when you get introduced to a brand new number E. 11. So, number E. You guys have always been told that letters aren't numbers. Well, yeah, there's a number that's a letter. All right. But it's kind of like a placeholder, kind of like pi is. It's like 2.68 something. It goes on forever and ever. It's like pi in a way. We'll get to that in a second. All right. So, now we're going to skip this warm up because that's just more growth stuff that you guys already know how to do. Okay. I'm not worried about that. So, compound interest is just saying that a lot of times with banks and money and accounts, they don't compound the interest annually. So all the growth that we've been doing so far has been in terms of annually, so yearly. All right. But more often than not, what banks do is that they compound that interest either quarterly, monthly, daily, whatever. All right. So in other words, more often than not, it's monthly. So for example, I have a savings account that I don't touch. All right. And it gains like 5% interest monthly, meaning it takes whatever it's in it at that end of that month, takes that 5%, that's what it gets compounded to. That's what gets added to it monthly. All right. So in other words, how many times a year is it actually doing? 12 times a year. All right. So the formula is kind of a modified version of the growth formula. Okay. So the compound interest formula is right here. So most of the letters still stand for what we know. So A is still the final amount. P is still the principal, which is the starting amount. R is our interest rate. Remember, it has to be a decimal. T is still our number of years. The number that's different is N, which is the number of times it gets compounded. So, for example, if I said monthly, how many times a year is that? 12 times a year. If I say quarterly, how many times a year is that? 4 times a year. All right, so these would be your N values, 12, 4, those would be N values. Okay, so whatever you're thinking of number of times compounded, that's just how many times per year are they doing it. So in other words, the formula isn't too bad. So, for example, we're going to do, So for example, we're going to know if we invested $500, 4% compounded monthly. Now, we're just going to do it over, let's say, 5 years. Okay? And we're going to compare it to when we compound annually. All right, so just to help us, we're going to scoop back up to the top real quick. I lied. We'll do one part of it. So 500, 4% annual interest rate. How much is it after 5 years? So exponential growth. So what we've been doing. So APRT. A will keep as A. What's my P value? 500. What's my R? 4% or 0.04. What's my T? 5. So I'm going to do A is equal to 500 times 1 plus 0.04 raised to the 5th power. Go ahead, put that in your calculator. Let's round it to 2 decimal places because we're talking money. So put in your calculator, round it to 2 decimal places because we're talking money. So it's 608.33. So that's how much money we have approximately after 5 years. Now, that is when we are compounding that interest annually, so once a year. Now, let's see how that differs when we compound it monthly. So how many times a year is that? 12 times per year. All right. So now, instead of using the growth formula, we're going to use this formula to plug everything in. All right. So I'm going to do like we've been doing with growth. We're going to define all of our variables first. So it's essentially all the same variables except you're adding on an n. So A is still A. What's my P? So what am I starting with? 500. What's my rate? 0.04. How many years do I want to go by? 5. And how many times am I compounding that interest? A year. 12 times a year. So guys, if setting up the formula is hard for you, start with this. All right, because then you're just replacing letters with numbers. So we have A is equal to 500 times 1 plus 0.04 divided by 12, all raised to 5 times 12. So all I did was just take the numbers that I came up with and plugged it into that formula. Actually, let me write this as 12 times 5. It doesn't really matter, but I want to make it consistent. Now, it's just like what we've been doing, just putting in your calculator, but be careful. Okay, so this is how you need to put it in your calculator. You do 500 times 1 plus parentheses 0.04 divided by 12, all raised to parentheses 12 times 5. So that right there is how you should put it in your calculator. So take a minute, do that in your calculator, and tell me what you get to the nearest decimal place. So exactly how I just wrote it, that's how you need to put it in your calculator. Otherwise, it'll screw up. Basically, I'm just saying, when in doubt, put parentheses. So every place I put a parenthesis, you need to put a parenthesis. Trinity, there's a new Delta math. That's pretty much it. All right, so I'm just going to put this in my calculator. So this is how you should put it in. I'm going to do 500 times 1 plus parenthesis 0.04 divided by 12. Close the parenthesis. Close it one more time. Raise it to parentheses 12 times 5. Close the parenthesis. So you should get $610.50 approximately. So $610.50. Now, how does that compare to the answer we got previously? Is it more or less money? More. Now, what you guys will actually find is the more time that passes, if you're compounding monthly versus annually, you're going to make a lot more money. All right. Now, it doesn't look like a lot now because we're only like at 5 years. But if you did 20 years, it'd be a lot more money, like thousands of dollars. All right. So that's the difference with doing those interest rates. So it's more money earned when compounded monthly versus annually. Now, to save time for these two problems, we're just going to set up the formula because then after that, it's just going to be putting it into your calculator. All right. So for letter A, let's start by labeling all of our variables first. So A is still A because we're trying to find that new amount. How much money did I originally invest for letter A? 1,000. What's my rate of increase? 0.03 or 3%. How much time is elapsing? 5 years. And how many times per year am I compounding that interest? 4. Why is it 4? It says quarterly, so that's 4 times per year. All right, take a minute, plug it into the formula. All right, you don't need to put in your calculator. I just want you to plug it into the formula. So we already got the variables defined, so I just want you to take a minute, plug that sucker into the formula. Thumbs up if you're ready. You're just plugging it into the formula. I'll give you one more minute. All right, check your answer. So, again, from here, you would just plug into your calculator, get a number, but the hardest part is putting it in the formula. So I just want to make sure you guys can put it in the formula correctly. So, without my help defining the variables, do part B on your own. So you just need to put it in the formula. So define your variables first, then write it in the formula.
Yo. We'll make 2.5. That's Wait, never mind. I've got it.
So you're just doing example B. You do not need to solve. I just want you to put the numbers in the formula. You died over here. Good Lord. Thumbs up if you're ready. One more minute. Good Lord. Y'all are nasty. How many times a year is that? How many times a year is that? My olfactory nerves are being assaulted, but that's okay. All right, so I'm gonna leave my A as A. What's my P value for this one? 5,000. Shh. What's my rate? 0.025. How much time is elapsing? Not 5. 15. Now, how many times a year am I compounding that interest? 365. It's saying daily. That means there's 365 days in the year. You're doing it every day. So, so A would be 5,000 times, guys, please stop talking. We're almost done. Times 0.025 over 365 times 365 times 15. It's lagging. Just give it a minute. Ugh. I disconnected it so I can reconnect it. There it goes. Stop. All right, so basically, the main things that you need to know is right here on this table. We're not going to fill in this table. I just need you guys to know what the end values are for these numbers. Those are the ones you'll probably see the most of in this class. As well as semi-annually. If I say semi-annually, how many times a year is that? Semi-annually. Half annually. So how many times a year is that? Annually is 1. Semi, think semicircle. How much of a circle is a semicircle? Half. So we're talking about half a year. So how many times is that a year? If they take it every half of the year? Twice. So that's the other one you need to know. Now, there's one last one that we got to do. Now, this is where that new number comes in. All right. So, when you are a famous mathematician, if you discover something, you really get to name it whatever the heck you want to name it. Well, there was this guy. His name was Euler. All right. And his name starts with an E. Now, he discovered this special number. Guys, listen. Now, he discovered this special number that he saw kind of as a constant, kind of repeating a lot within specific mathematical scenarios, mainly in exponential and logarithm stuff. All right? Now, it's just like how pi you see a lot with circles. All right? It's like the number pi you see a lot with circles. The number e you see a lot in exponential and logarithmic functions. Now, since his last name started with an E, he's like, I'm just going to name it E. And thus he did. All right. So E is actually a number. All right. Now, E is used as a base in modeling exponential situations. And it involves continuous growth or decay. Now, the way we use it in this class is for situations where it says compounded continuously. All right, so we're still doing compound interest, but we're using compound continuously. And this right here is the formula. A equals P E raised to the RT. All right. Now, A is still your same thing. A is still your final amount. P is still your principal. R is still your rate. T is still your time. However, E is a number. And that number, if you actually put it in your calculator, so in your calculator, you have an E key. It's right here. So if you hit second and then the division symbol, it will generate E. So second, there's E. It is not a variable because watch what happens when I hit enter. It's actually a number. So E is approximately 2.71828. All right. Now, just like how pi is 3.14 approximately, E is 2.72 approximately. Now, I don't expect you to remember that. You just got to remember what E is, and that E is a number. Your calculator will do the E calculation for you. Okay? So E is equal to approximately 2.71282. Approximately. But it's a number like pi that goes on forever and ever. So, congratulations, y'all discovered a new number. So, again, E is just a number and it's similar to pi. All right, so you guys know how we use pi to represent 3.14, et cetera, et cetera. E is just another number that's like that. It's just an irrational number that goes on forever and ever, but we just see it as a constant a lot in certain scenarios, specifically exponential and logarithms. All right, just how pi is seen a lot in circles and trig. And by the way, pi is technically a letter too, just in the Greek alphabet. They, there were just people that would just sit for hours just doing this stuff, and there were no calculators back then. So think about that. Some people were just like that. Now, shh. Last thing we're gonna do, we're just gonna do one last problem, but just the continuously one. So we're just doing this one. Guys, it'll take us like 2 minutes if you shut up and let me do it. So we're just doing part E of number 1. I just want to make sure you guys understand the continuously, how to put that in. So you use the formula PERT. So PE raised to the RT. So 10 years, $15,000, 6% interest compounding continuously. So A is still A. P is going to E equal to 10,000. Is it 10,000? No, it's 15,000. I lied. T is going to be equal to 10. R is equal to 6%, which is 0.06. And we're going to put all of this in the formula. A equals PER to the T power. So if I put this in my formula, I have A is equal to 15,000 times E. I'm just going to write the letter E. And I'm going to raise it to 0.06 times 10. Now, this is how you're going to put it in your calculator. So, in your calculator, I'm going to do 15,000. Now, so I don't have to actually put in E and then raise it to a power. There's a key that will actually raise E to a power for you. So, if you hit second, and then the key to the left of the number 4, it says LN on it. That will give you an E, and it'll already raise it to the power for you. So I'm going to hit second, LN, and I'm going to type in parentheses, guys, hush, 10 times 0.06. And I actually get a number. So after 10 years, we will have $27,331.78 if it's being compounded continuously, meaning it's not a certain number of times per year, it's always just keeps going. So A is equal to 27,331.78. And again, I know PERT is going to be the easiest one to remember. You can only use PERT if it says the distinct words compounded continuously. If it does not say compounded continuously, do not put it in PERT. If it says compound monthly, that does not go in PERT. If it says compound daily, that does not go in PERT. Doesn't go in PERT. PERT is strictly compounded continuously. Otherwise, it goes in the other formula we just learned. All right, guys, listen up. So, sorry class went long today. Tomorrow's lesson's not going to be nearly as long. I just had to get through this one today, so I had to kill you just for today. All right? There is a new Delta Math, 2.2 Delta Math. All right? So if you have time later, make sure you get started on it. But I will give you some work time tomorrow as well. So y'all can go ahead and pack up. Make sure your whiteboards are erased. Make sure your calculators are put up.